Okay, I think we'll get started. So today we're going to talk about the common ion effect, which is a manifestation of Le Chatelier's principle, and it also forms the foundation for buffer solutions, which are really important in many, many cases, particularly in biochemistry. Our body is one big buffer in many ways. If we add extra acid, our body will buffer that acid and not change the pH so much. There's all sorts of other buffers too, not just pH buffers. So we'll be talking today and the next lecture specifically on buffers. But the key idea here, the underlying idea here, is the common ion effect and the Chatelier's principle. So let's say we have a reaction, and this could really be any reaction, but we'll stick with acid reactions here. So we have an acid dissociation reaction. HA goes to H plus A minus. And now we're going to add H plus or A minus. Doesn't matter. In our examples, we'll add H plus. Then by Le Chatelier's principle, we should send our reaction back the other way. So let's work through some examples. Let's say we have 10 mils of 0.01 HCl is added to a niacin solution. Okay, so our job here, first thing we need to do is, because we've changed the volumes here, let's get the new molarities before any reaction has happened. So we imagine adding these, then boom, what's the molarity? So molarity of niacin, here's our original amount, our 25 mils. Here's our molarity, and then there's our new amount. We could just as well have done M1V1 equals M2V2. And we get a new molarity of niacin. The molarity of H plus is going to be exactly the molarity of HCl because it's a strong acid. So whatever the HCl molarity is, we'll just take that to be our H plus because it's fully dissociates. So we've got 0.01, that's our 10 mils, and 0.01 is our, so I guess two numbers the same here. 0.01 is our molarity of our HCl solution. So that gives us a new molarity of 0.0082. Sorry, 28, yeah. So that's a dilution factor for this, this HCl. Okay, so what do we do now? We now have a situation where when we write the ice chart, we've got this is common to the ice chart. So once the H plus breaks up away from the HCl, it doesn't care if it came from the original niacin or from the HCl, it's just HCl. So this H plus, it doesn't care if it came from the original niacin as an H plus or from the HCl. It's just a plain old H plus. And so here it is sitting in common with this. And so in our ice chart, we just have to take how much H plus is around. Doesn't matter where it came from. And so we, instead of having 0 here for this acid dissociation reaction, we actually have a common H plus. And that's going to influence where the equilibrium lies via Le Chatelier's principle. So we calculate things as normal. Here's our Ka for this. And then we've got our 0028 plus X, because this is a product. So we've got a plus X up on top here, and then times X, that's just our conjugate base, and then our original niacin minus the change. The physical value of X is 3.2 times 10 to the minus 4th. And so that does change things a little bit, and we get a pH of 2.6, which is going to be a little bit shifted more back this way because we've added a product. All right, so we see that the common ion ultimately just shows up in the ice chart. There's some work to do to figure out, the new molarities and stuff, but otherwise it's just an ice chart like normal. So let's talk about this role in buffers. So pH buffers, for example, this will be a pH buffer. What we do here is we use conjugate acid and base pairs because then we know that they're going to have common ions. And now instead of this example where the common ion was the H+, now the common ion is going to be the conjugate base. So let's take an example of an acetate buffer. It's a very common buffer. So we're going to use acetic acid, and so we're going to use acetic acid and sodium acetate. So we pull acetic acid off the shelf, we pull sodium acetate off the shelf. Those are conjugate acid-base pairs, and we make up solutions of each. Let's make up 0.1 molar solutions of each, and we don't need to add that, we can add them in any amount here. Let's add 25 mils of acetic acid solution and 15 mils of the sodium acetate solution. And then we'll want to know the Ka for the sodium, for the acetic acid. So the new concentrations we have here now are calculated. Here's our original 25, here's our concentration, and here's our new amount, 40 milliliters. So that gives us right when we pour the solution into the beaker, before the reactions happen, this is our molarity of our acetic acid. Likewise, very same calculation, this is the molarity of the acetate. So go through, get our molarity of our acetate. Okay, so we're thinking about this. This is right before any reactions happen. So that's our initial conditions. We have now some common ion here. So in the acid dissociation reaction, we've now added some conjugate base deliberately here under our control. So we can control how much of this we add. We can write our ice chart, and we solve, and we get x equals 10 to the minus 5. Now, let's calculate how much of each of this is around. Well, we're going to have 0.063 minus this, but that's going to be inconsequential to sig figs here, right? So essentially, it doesn't change. It's so little. And likewise, same here. This is not going to change. So this would be 3.038 plus x. Well, it's still going to be 0.038. But what does matter here, what is a significant change, is going from 0 to x is H+. And so we take the log of this, and we get a pH of 4.45. So what we've done here, we would say we have made a sodium acetate, so we've made an acetate buffer designed for a pH of 4.55. So what it's going to do is this is going to try to hold the pH at 4.55 via Le Chatelier's principle. So if we add a little acid, right, this is going to buffer that effect and not have the pH change very much. Likewise, if we add a little base, this is going to buffer the pH change and not have the pH change very much. So let's go ahead and do that. Let's add a little acid. Let's see how much the pH changes compared to if we just had pure water. Okay. So let's now add 10 mils of 0.01 molar HCl. Now, this does bring up something. There's a buffer capacity associated with this. We cannot, what's called, overwhelm the buffer by adding more or a higher concentration of H plus or OH minus than what we have in our initial buffer setup. So if we want to be able to handle larger amounts of acid being added, then we're going to have to increase the concentration of each of these. And we always want these to be way bigger, or quite a bit bigger anyway. It doesn't have to be way bigger, but say 10 times bigger than the amount of acid we're adding. So we're kind of there, right? So this is a lower concentration, and we're only adding 10 mils, and we have 40 mils of solution there. So we're in the ballpark of about 10 times less. So we should be okay. We should not overwhelm this buffer. Our pH should stay pretty close to 4.5. So that's something you do want to kind of check. Are you adding too much acid, especially if this is in a lab setting where you need to prepare a buffer and have it work for you. All right, so let's figure out, we got to go moles now. So let's figure out the moles of H+. So we've added 10 mils of HCl, and this is our molarity. So this gives us 0.0001 mole of H+. We have this concentration of acetic acid, right? Because we're saying this didn't change much here. So this is our original concentrations that we've added. And so here's 40 mils, and this is our moles of acetic acid. And so there we can see we're about 25 times more moles of acetic acid than H+. And likewise, we're about 15 times more moles of acetate. So we should be okay. We should not see too much change in our pH here. So let's check that out. All right, so our new moles, what are we going to do? We're going to say that, again, we're going to slam the reaction all the way over and then watch it come back to equilibrium with an ice chart. So we've added H+. That's going to drive the reaction back this way. So we've added H+, drive the reaction this way. So we're going to drive it all the way back. So that means our new number of moles is going to be this, plus for every mole of H+ we've added, we're going to drive back and make 1 mole of acetic acid. And so we're going to have a total now of 0.0025 plus 0.0001, or 0.0026 moles of acetic acid. We're going to consume, when we do that, we're going to consume exactly that many moles of the acetate, conjugate base, and so we're going to subtract that, so we get 0.001 mole of acetate. Now these are moles now, so we have to go back to concentrations. Our new volume is the original 40 milliliters of buffer and 10 milliliters of the acid. Very easy to make the mistake and forget to keep track of the total volume as you add these together. So total volume is 50 here. And let's calculate our new molarities. And so there we are. I didn't show the full calculation for the acetic. It's just like this. It'd be this divided by 0.05. And so we get 0.028 molar. All right, well, let's set up our ice chart. There is our starting amounts of concentration. 0 in H. Why is that? Because we've slammed it all the way the other way. Now it's going to come back this way. So we get our change of x, minus x, x, and x. We write our K equation. So here's our Ka, products over reactants. The physical solution here is 3.1 times 10 to the minus 5. That is the H. So the new pH is 4.50. So we've changed by 5/100ths of a pH. And so this buffer has worked pretty well. We added a strong acid, and yet our pH didn't change very much. And that's the role of a pH buffer. We see it working here. Let's compare that to no buffer. So water is a terrible buffer. And so we add 0.0001 mole of H+. That's how much we've added. What's the new volume? 0.05 liters or 50 milliliters. That gives us a concentration of 0.002. And if we take the minus log of that, we get a pH of 2.7. So a pretty massive swing in this pH. And so we see water is not a good buffer. So putting that into pure water, not a good buffer. All right, so buffers are very, very important. You see the calculation is a little bit elaborate, although you are certainly at this point, if you've been practicing along, quite readily, easy, can handle this pretty easily. But we will learn a shortcut next time called the Henderson-Hasselbalch equation, and that will help us calculate buffers pretty quickly.